Okay, there are many exponential functions. Y equals 2 to the x, of course, is one of them, and we know what its graph looks like. I've drawn that graph over here. And it's our basic exponential function. We've drawn that many times by now, I would hope. Okay? Well, in general, exponential function is of the form y equals b to the x, where b is any number greater than or equal to 0. Now, I've written 4 examples of exponential functions that give you kind of a picture of how they behave for different bases. B is called the base, and for different values of b, preserve our battery, for different values of b, we get different exponential functions, different behaviors. Forgot how that sentence was really going to end when I got distracted. Okay, so we can easily make a table for, let's say, y equals 3 to the x. A whole lot like the table for y equals 2 to the x, except, of course, we're taking powers of 3, and you can verify that these are the values. This should be completely obvious if you understand why the values of 2 to the x are what they are. Values of 3 to the x are really easy to understand. Okay, so we can then sketch the graph of y equals 3 to the x. Here it is. Okay, I don't have to explain to you how this was done. We just graph the points in the table and sketch a curve for the extended kind of basic 3 to the x function. Okay? So, in terms of 2 to the x, it's easy to understand the 3 to the x function. For negative numbers, 3 to the x is going to be, for negative values of x, 3 to the x is going to be a lot less than 2 to the x. And the less your x value is, the smaller the 3 to the x value will be compared to the 2 to the x value. You should check that out, make sure you understand that statement. And for positive values of x, the larger the positive exponent, the larger the positive value of x, the more the 3 to the x function is going to exceed the 2 to the x function. Or we could say the greater the ratio of the 3 to the x function to the 2 to the x function. There's plenty I could say about that, but let's stay focused on the idea of these graphs. Okay, so let's see. Now, 1/3 to the x and 1/2 to the x. I'm not going to do the arithmetic for you, but if you make a table for 1/3 to the x and 1/2 to the x, for example, I wasn't going to do this, but I will. Just a little example here. 1/2 to the -2 is the reciprocal of 1/2 squared. And of course, I'm assuming strong algebra skills here. If you don't have them, make sure you completely review the laws of exponents and, make sure you're aware of them. So this is 1 over 1/4, which is 1 times 4 over 1, which is 4. Okay, so as an example, 1/2 to the -2 is clearly 4. And using this example, imitating this example, you could do 1/2 to the -1, 1/3 to the -2, 1/3 to the -1. The positive powers of 1/3 and 1/2 should be pretty obvious. And when we calculate those and do the table, and if you're not totally clear in this, if you can't do it in your head, write it out. The graph of y equals 1/2 to the x is going to be here. Here's our value, -2, 4. Here's our value, -1, 2. Here's our value, 0, 1. And of course, any b to the x, whatever b is, whether it's 1/2, 1/3, 2, 3, 75, when we raise it to the 0 power, we're going to get 0. So, all these graphs are going to pass through the point 0, 1. And then the rest of the values should be pretty obvious. So we get a graph that looks like this, and it's just the reflection of the 2 to the x graph. If we take this whole thing and flip it over this way, the 2 to the x graph will become the 1/2 to the x graph. Similarly, 3 to the x graph is symmetric with respect to the y-axis. with the 1/3 to the x graph. Flip it, and the picture looks exactly the same. Okay, so there it is. Now, the one thing that's going to be very relevant, because what we're doing is we're moving into analysis of finance, which will also give us some idea of how population models, epidemics, and so forth behave, radioactive decay. We want to look at the graph of y equals e to the x, and we're going to explain where e comes from and define it. Okay, y equals e to the x, which approximately is 2.7 raised to the x. It's not difficult to do powers of 2.7. 27 squared, everybody knows, is 729, and so 2.7 squared is 7.29, about 7 1/4. And 7 1/4 is actually a better approximation to e to the x, because this number here is just a little bigger than 2.7. Well, without going into detail, 2.7 to the x, we would expect to have a graph that's between 2 to the x and 3 to the x, wouldn't we? 2.7 to any positive power is going to be less than 3 to that positive power and greater than 2 to that positive power. So we would expect the graph to be somewhere in between the graphs of 3 to the x and 2 to the x. And we would probably expect it to be a little bit closer to the graph of 3 to the x, because 2.7 is a little closer to 3 than it is to 2. Now, there's nonlinearities involved, and how much closer is a little bit complicated. We're not going to trouble you with that right now, but that's kind of what we'd expect. So we'd expect a graph maybe somewhere along here, and then it's going to be squeezed in between these two. Now, I can easily estimate 2.7. If this is, the y value here is 2, the y value here is 3, so 2.7 would probably be about here. And then we square 2.7, we get 7.29. Well, if this is 4 and this is 9, halfway between 4 and 9 is what? 6.5. 4 and 9, 13, 6.5. And 7 is going to be then a little more than halfway between here and here. Not as close as you might expect, because squaring it, well, again, there's a nonlinearity there. I'm not going to really comment on it, but we get a point like this maybe. And of course we have this point, and then the graph has to be in between these two. It's going to be a little hard to do that precisely, but I'll try to stay a little closer to the 3 to the x graph. But then, things get a little messy here, because the lines kind of merge. And of course they have a finite thickness, but we get a graph like this. Okay, so this is the approximate y equals e to the x. Now we're going to see next where e comes from and why it's so important. One reason it's so important, of course, is you have an e to the x button on your calculator. Why would that be? Turns out that e to the x is a function that has some unique properties that are very handy when you're doing calculus. And since the whole world is run by linear algebra and calculus, this is important. So, I'm going to look at that a little more closely.